Away you go.
All right.
Hello, hello, hello.
Yeah, what's wrong?
Yeah, start.
Can you hear me?
Yep.
Yeah,
All
we
right,
can hear
easier.
you. Off you go.
Yep. Mathematics can be described as a conceptual art that prevails truth, one that is developed with subsequent reasoning, a well-constructed method built on validity, as well as being an invariable language understood globally, having the congruency to unite all. There have been many renowned and accomplished mathematicians and scientists embedded within our history that have paved the way towards many mathematical advances for modern era experts, advances that were once deemed impossible hundreds of years ago. One example is Archimedes, who was arguably the greatest scientist of the classical age, and without his extraordinary work, integral calculus would be impossible at this day and age. Born in Greek city-state of Syracuse in approximately 287 BC, Archimedes has always been fond of curves and had always been determined to learn about the recurring indices and how these indices would allow different curves or shapes to relate to each other. He decided to utilize this passion and investigate the properties of a sphere, one of the simplest yet complex shapes to ever exist. Simple to look at, but packed with abstruse characteristics. Examples of such are its two-dimensional measure, its surface area, as well as its three-dimensional measure, its volume.
To begin with, Archimedes' drive and ambition, as well as his love for this complex area within mathematics, navigated him straight to his roots. Using the method of exhaustion, developed about a century earlier by one of Archimedes' heroes, Euclides, the surface area of a sphere changes its direction at every point, unlike that of a cube, which has edges and corners present to allow its direction at every point, which shoot, and corners present to allow its properties to be determined far more easily. Archimedes started off this investigation by developing a thought experiment where a sphere is sliced in half to produce two hemispheres of the same size and magnitude, giving him a flat surface where he is able to begin his calculations with. He then imagined placing a hemisphere down on a flat surface, fitted perfectly inside a cylinder with the same radius r and height h as the radius r of the hemisphere as shown in the image. With a gifted mind as well as the immense determination to find an answer to this investigation, he was able to construct an incredible idea similar to modern-day integral calculus, where he imagined slicing the hemisphere cylinder hybrid shape horizontally into somewhat salami shapes, a method vaguely identical to mechanisms within equations such as trapezoidal and Simpson's rule, which were taught during high school to determine area under a graph. He began the slicing from the top, where the resulting slice produced the smallest possible hemisphere, possible within an intentionally small radius as compared to the slices to come once he moves down the shape. After this process of continued slicing and producing an increasing size of the resultant hemisphere, and this this comparing it to the constant size of the cylinder around it, Archimedes aimed to determine the size difference in the gap between the slice shapes. The gap between the hemisphere section and the cylinder section of the slice shown in the figure in blue. From each slice, he calculated the area of this gap to determine the volume of this slice. He then added the volumes of these slices with different sizes of hemisphere, yet the same size of cylinder, and ended up getting the volume of a cone, which is 1/3 pi r squared h.
This allowed him to get a step closer to solving the mystery of the volume of a sphere, as the volume of the cylinder minus that of the cone would give him the volume of the hemisphere. This is shown in the equation. Volume of a sphere equals pi r squared h minus 1/3 pi r squared h. This will give 2/3 pi r squared h. Here, we know from before that h equals r, as the hemisphere had to fit perfectly inside the cylinder. This sums up the answer from 2/3 pi r squared h to 2/3 pi r cubed. When we double this formula, we will get the volume of a sphere as it is currently in the format of that of a hemisphere. The resulting formula derived by Archimedes was 4/3 pi r cubed. From these results, he developed a theorem known as Archimedes' hatbox theorem to determine the surface area of a sphere, which states that for any sphere section, its lateral surface will equal that of the cylinder with the same height as the section and the same radius of the sphere. This means that the total surface area of a spherical object is equal to the curved surface area of the circumscribing cylinder. Mathematically, this can be proven in the following formula using this image. Here we see that the surface area of a sphere is equal to the surface area of the curved area of the cylinder, which is 2 pi r h. We know that using the image h equals d, so the diameter, which equals to 2r. When we substitute 2r into the equation, we are left with 4 pi r squared. These investigations led to a universal acceptance and appreciation of Archimedes' work and cemented his experimental discoveries in the history of mathematics. In today's age, we are still working with and using to our aid the formula V equals 4 over 3 pi r cubed and surface area equals 4 pi r squared. One thing you may notice about these formulas is that the formula for the surface area is a derivative of the formula of the volume. This can be explained using a simple thought experiment. We know using derivation that the rate of change of volume over radius equals the surface area as shown in the equation here. Now imagine a sphere is covered externally with a layer of paint. This will add to the existing volume of the sphere, as the layer of paint has its own volume as well. Now if the external paint has its own surface area and the volume of the sphere has significantly changed, then the rate of change of this volume, which is the new volume minus the old volume, will equal the surface area of the added layer of paint. This relationship also holds for higher dimensions as well, as this discovered by Leonhard Euler. The n-dimensional volume, n is any integer, of a Euclidean bore of radius r in n-dimensional Euclidean space is this formula, where T is Leonhard Euler's gamma function. The n-dimensional surface area on a similar layer is equal to this right here. Here we see that the formula illustrated above of the surface area consists of a change in volume over the change of radius. This proves the fact that the relationship between the surface area and volume of a sphere also exists in higher dimensions, that of a Euclidean ball in a Euclidean space. With the exceptional efforts of Archimedes during the classical age, the 21st generation is able to solve complex problems and inconsistencies with theories using the experiments and discoveries he put forward from mathematicians such as Leonhard Euler and many more to come. Thank you.
Okay, thanks very much, guys. Is that the end? Now, could you just confirm for me? I heard Rafi, Mohammed Mansour, and did I hear Othman in the last there?
Yeah, that was awesome.
Okay.
Yeah.
All right. Thank you, guys. Any feedback for anyone? Anybody got anything positive to say, please? Any questions? All right. We've only got 90 minutes in this time slot, so we've got to keep moving. There's a few of you that want to do their work, so well done, guys.
Thank you, Jason.
Just
Thank you.
unshare that now, please. You can leave now if you want to. All right, so we've got a few people that have got queues, and the next one I'm allocating, I will tell you when you're next. Okay, a couple of you have asked. So Yowzi, you're next. If you could get yourself organised, please.